Hello, everyone. This is Dr.Hira, and our today's discussion is about enzyme catalysis. Before this, we have discussed about the bioenergetics, and now we are taking up that concept further to apply that how the reactions get catalyzed in the presence of the enzymes. So, what are our objective for this discussion is that we will see define what the reaction equilibrium. Though you have, I hope you have get that concept what equilibrium is, but we will see with example and mechanistic approach and with an application that what are the reaction equilibrium. Uh, how to determine the reaction spontaneity based on the free energy of the reaction coordinates, how a catalyst reduces the activation energy to speed the rate of the reaction. And finally, we'll also see that how what is a mechanism that enzyme stabilizes as transition state to decrease the activation energy of the reaction, because that we know from the chemistry point of view and from the biological discussions that the catalysts do decrease the activation energy of the reactions to make it feasible at the faster rate and with reduced hurdle, or we will talk about that one. So the very first thing is that the biochemical reactions, like any chemical reactions, always proceed towards equilibrium. So the equilibrium is basically the phase, you can say, or the stage where it maintains to reduce the entropy of the system, and they are balancing the reactants and the product to a level where they are maintaining the system. So in the technical terms, what the equilibrium state is, so that is to a state where there is no net change in the concentration of the reactant. So usually what the students misunderstood, but usually people do understand, and maybe in our undergrad level, we also have developed that concept that equilibrium is some kind of state where the concentration of the reactant and the concentration of the products are the same. No, that's not true. That is totally the wrong thing you are um, getting up, or you're making up your mind. So the concentration is not necessarily equal. It is basically that the net change in the concentration of the reactant is in the concentration. So is zero, right? Or it's almost zero one. So they are balancing the product one. So that you have to keep in mind. So there is no net change in the concentration of the reactant. This is not about where the concentration of the reactant and the product are the same. So they are balancing to the system in an equilibrium, that they wherever something is getting higher, so that will move forward to the direction where it can balance with the production of the product, or maybe to reverse to the reverse reaction to the formation of the reactant one, right? So if you just look at this reaction, so we can see, and from this we can also, and I had told you that what our objective is, that we can determine the spontaneity or spontaneity. So the people do pronounce it in a different ways. So as visible to you. So the spontaneity of the reaction, the state of being spontaneous, can be determined by looking at its free energy, or the um, delta G prime value, right? And we can also determine that in what direction that reaction will proceed. So the very first thing is, if you just look at this graph, so here this is a free energy and the reaction coordinates on the x-axis, and we are examining that this is the one-step reaction where a substrate is converting into the product one. So there is a one transition state which is formed, right? And we always know that this transition state is basically the barrier, and this is the most challenging step that the substrate has to overcome this barrier in terms of the activation energy, and then it will convert into the product. Now, if you just look at in this particular example, here you can see that substrate has this level of free energy. And if you just look at the product, this is having the free energy at this level. So it means the substrate has the higher free energy value as compared to the product. So during the reaction, when the substrate converted into the transition state and finally it goes to the product, so there is that amount of energy delta G, which is a difference between the substrate level of free energy it already had, um, it inherit, and it is converting the product. So that is a delta G, right? If the substrate has a higher and the product has a lower one, so what we assume that there is the amount of energy which will release, and the release of energy we mentioned with the negative sign. So the reaction is spontaneous, and we know if we have the delta G less than the in a minus sign, so this reaction is basically the spontaneous one, right? So here, this delta G prime naught is the negative one, and this is giving us about the reaction, either that is a spontaneous or the non-spontaneous. What if we have the delta G prime naught as a positive one? It means that the product has the higher level of energy, free energy content rather than the substrate one. So then the substrate has to gain that certain amount of energy to convert or to be at the level of the product one. So then it would be the positive delta G value. So this would be the non-spontaneous reaction, right? Means this is not favorable just by the release of the energy. We have to do some extra work on the substrate to be at the product level. And another way, the system with the higher energy is more challenging as compared to the system with the lower energy. So once the substrate has already its a higher energy, and for the product conversion it has to be lower, so it means it's favorable for the system that be it will gain the lower energy level. Now, the next thing is there are the external factors which can affect the equilibrium. So, for example, rate of consumption of the product, that how many products are consuming during the reaction. So, if there is a high rate of the consumption of the product, so the reaction will move into the backward direction. So, the consumption of the product in a subsequent reaction will change the equilibrium. So equilibrium will shift according how much rate of the consumption of the product is there, or the formation of the product is there. So it means that these both external factors, the change in the equilibrium and the rate of consumption of product, and the thermodynamic parameters can tell us something about the spontaneity or the directionality of the reaction, but cannot tell us anything about the speed at which the reaction proceeds. So the speed of the reaction is determined by the catalyst of the reaction. And we will see, and we will compare the example at how we say that enzymes or the catalyst do affect the speed of the reaction. So the biological catalyst will increase the rate of the reaction by 5 to 7 orders of the magnitude. Why? Because biological catalyst has to work in a very delicate system, and the biological catalyst, which are largely the enzymes, and they are in protein in nature. Very few are the RNAs, but usually they are protein in structure. So we have the example of the RNA as an enzyme is in the replication of um, the DNA. When there is a formation of a protein and there is the um, messenger RNA and the translation RNA, who is basically joining these amino acid, and they are combining these one. But otherwise, they are largely they are protein in structure. So they have that kind of enhancement or the magnitude in terms of the speeding up the reaction, while we see a lot much higher rate in the laboratory or general chemistry catalysis reactions, where this do enhance up to 10 or more than 50 times, right? But in biological catalysts, they do increase the rate of the reaction by 5 to 7 orders of the magnitude generally. Now we will see an example. This is the reaction, and this is the first step of the glycolysis. So glycolysis is a you can say that the addition of the glucose in our biological system, and we will see that glycolysis and discuss that in our future lectures in detail. I have picked this one example from the first step one because that will be easier for you to relate with your next lectures, and you can understand that you can apply that one. So here, this is the first step of the glycolysis, in which in a very first step of the decomposition of this glucose, how this digests into the carbon dioxide and water. So the very first step is this one, that this glucose with the ATP in the presence of hexokinase is an enzyme which is catalyzing this reaction. This converted into the glucose 6 phosphate. So there is the replacement of this phosphate over that side, right? So this ATP is donating, because this is adenosine triphosphate, this is donating the one phosphate group to this glucose, and then obviously that is losing one of its phosphate. So this is the adenosine diphosphate now, in the product tab, right? So this reaction has the delta G value minus 16.7 kilojoule per mole. So what do you assess from this one? Is this spontaneous or non-spontaneous? Yeah, take a moment. Yeah, so that is a spontaneous reaction, because here the amount of energy is releasing. It means that substrates has the higher energy as compared to the product one. And ATP, we know this is called as a cellular currency, and or we are being the chemotrophs, and we utilize energy in the form of the chemicals, and then we perform our cellular activities. So this ATP is our energy form, and our body do recognize and do accept energy in the form of the ATPs. So this ATP then reacting with the glucose and working with the glucose in the presence of a hexokinase, it is converting this glucose into the glucose 6 phosphate. Now we have to see that what is the importance of the hexokinase, and do really there is a difference between the reaction of the glucose with the ATP in the presence or in the absence of this hexokinase enzyme. So we can see, so here if we do assume that we have the test tubes, and uh, in one there is only the glucose and ATP, and we are leaving that reaction only on the basis of their collision, right? And there is no external factors. Now in a next one, what we do is that we are keeping the concentration of glucose and ATP same, but we are adding the hexokinase here. So the one is with the presence of the enzyme, and one is with the absence of the enzyme. So we will see what happened. So when that was studied, so the rate of the reaction in the absence of enzyme was 10 raised to power minus 13 moles per liter per minute. And when that was compared with the reaction with the presence of the enzyme, the rate of the reaction was elevated to the 1.3 times of 10 minus 13 moles per liter per minute. So what does it mean? It means that is the 10 to 10 times faster with hexokinase. And obviously, our body cannot afford if it has to go for with that um, rate of the reaction. So here the things are happening in a seconds, nanoseconds, and they are thoroughly controlling that complex system. So that is a blessing of the nature, that they have created such wonderful enzymes, and they are doing that job in a just a blank or the in a such a faster rate that they are fulfilling our requirements and our needs, right? So overall the reaction will be 10 billion times faster in the presence of enzyme than in its absence, in case we have compared the glucose in the presence of the hexokinase, or in the absence of the hexokinase, the conversion of the glucose into the glucose 6 phosphate. Now that we have established that the enzymes do catalyze the reaction, and they do affect the activation energy, they enhance the rate of the reaction. But what actually the activation energy, and why we need the activation energy? So the activation energy is basically is the amplitude of the activation energy, or you could say the energy required to fulfill, to overcome the barrier, right? I can just give you the example of your life. So you have certain goals in your life, you have an objective. Some of you may want to be a businessman or a businesswoman. Some wanted to be a professor, some wanted to opt a research job, an industrial job. So you all have certain objective, but this is not the case in your life, that you just dream, you just think about this one, that you wanted to be like this, and eventually you will be there. No, this is not. You have to work for this, you have to modify yourself, you have to get skills for that one. So there is adaptation, there's a transition, there are the changes, there are the acquiring of certain skills you need to be at that position. So that is what a reaction needs. So when there is a substrate and it has to be converted into the product, so there are the certain bonds that have to rearrange. There are the transit chain charges that are formed on the enzyme, because we know there is the amino acid, and let's say there is the amino acid, right? And we know plus or any of the compound, right? So I can just write at the moment substrate. But in a more technical way, let's say this is the enzyme, and we call our substrate as a ligand also. When we talk about the drug discovery and the medicinal chemistry, and we examine that how our compounds do affect or do bind with the enzymes one. So right now, because we are using these things, so we will say this one, right? Enzyme is bonding with the substrate. So there in this enzyme is made up of the amino acid, right? So there is a certain amino group, there is the alpha carbon, there is the R, there is the hydrogen, and there is the carboxylate side, right? So if I just can say this one, so obviously that compound has certain functionality with which that will bound to that amino acid, right? And that particular amino acid will be in the enzyme's active site. So there will be these certain charges will develop once they are making the bond rearrangement, and when the enzyme hold the substrate through the non-covalent interactions, so it is binding that substrate. So obviously because of that interaction, that may get partially negative, some get partially positive one. So that transit charges will be formed on the enzyme, distortion or change of the position of a chemical group, and so on. And a spatial rearrangement, if this is around the sigma bond, it has to change its conformation, certain group to the backside or front side, to be too adaptable towards the substrate and the active side of the enzyme one, right? So in fact, the activation in energy is the amplitude of the activation energy that determines the rate of the reaction. So higher the activation energy is, slower the reaction will be. The lower the activation energy is, the faster the reaction will be. Why I say this? Um, let's say, and I just have to remove that what I have drawn here. This. So just to make it clear for you, right? So here we are comparing the two graphs, two reaction coordinate diagrams with you. One is the normal, right, where there is a reaction and in the absence of the enzyme, and now here you can see this is the in the presence of the enzyme. So what we know from the induced fit model of the enzyme substrate binding and the action of the enzyme we have studied in chem 330, that there is the substrate, then when it bounds to the enzyme, so there is a enzyme substrate complex, there is the enzyme product complex, and finally there is the end product which will be released into the system, and enzyme will be um, in the system uh, after catalyzing and facilitating the reaction being unconsumed, right? So what enzyme is doing, when enzyme is making these complexes, right, with the substrate and the product, so this is basically facilitating, this is adapting, this is binding this substrate with itself to make it at a level that it has to make the rather the less harsh adaptation, and it is bringing that activation energy to the down of this, right? So this is the um, enzyme substrate complex, and this is a transition state, right? And then eventually after lowering that energy, it will finally on a stable form, which is the electro enzyme and proton product complex, and then eventually finally the product is there, right? So here you can see that this substrate to this level, this is a certain amount of activation energy, and from this substrate to this was the transition state, right? And that was the normal without enzyme. Now what is the difference between these two is that this amount of energy from this has reduced, right? And this reduced activation energy is also called as the binding energy, right? And that will release once the enzyme is bounding with that substrate. So this is a mechanism that the nature had developed, that this binding energy, this energy is released. Um, and this release of energy is basically facilitating to lowering the entropy, to lowering the activation energy for the transition state, and make it feasible and make it viable at a more faster rate, at the more lower activation energy. So eventually that is at the faster level, right? So that we infer. So if this gap is higher, so we'll have the slow reaction when this activation energy is lower, and then we have the faster reaction. So that what exactly the enzyme do is that it lowers the activation energy of the transition state. So that was the end of this concept, that how the enzymes is catalyzing this reaction, right? And what is the difference between that one? So after this lecture, I have a assessment question for you, and then we will proceed from that to see another catalysis examples, and we'll apply that one. Okay. So if you have any questions, just comment on the video, or you can just email me. Thank you. Have a good day.